Welcome to this new topic, sound waves. So when we started looking at waves, the first type of wave we looked at was the general wave. Then when we were done with the general wave, we have gone to sound waves. After sound waves, we're going to finish waves with what is called light waves. So this topic is going to be delivered in the following way. We're going to start with introduction to sound waves. Then we'll move to the speed of sound. We're going to discuss two methods of measuring the speed of sound. Then after that, we're going to look at other properties of sound waves. So there's an error here, it's sound waves instead of sound waves. Anyway, let's get started. Actually, this is a very short topic, so I hope you're going to enjoy. So let's say there is an audio source here or something that produces sound. So what happens here? So when sound is produced, what happens is this part of the speaker is going to vibrate back and forth. This vibration is going to cause the nearby air molecules to vibrate back and forth. These air molecules, when they move back and forth, they are bumping into the neighboring air molecules, and this process is going to continue till the sound propagates through the medium, which is air in this case. So generally, let's say we have got Mr. Boy here who is speaking to another Mr. Boy here. So when they speak, the sound waves can be pictured like this. So if you see here, what's happening here is there are molecules which are moving back and forth, bumping into each other till the sound here reaches here. One thing you should know is the actual molecules are not moving, but the disturbance is the one that's moving. The disturbance are propagating through a medium is defined as a wave. So the particles here, they're just vibrating, but they're not moving. Then the neighboring particles are also vibrating. When the particle here hits into another particle here, this particle is going to move, just like this was moving. So this will continue, but the particles themselves do not move. So the wave is going in this direction. Therefore, the direction of propagation of the wave is to the right. Also, the particles are moving left, right. So they are kind of parallel or in the same direction, if you may. So the direction of vibration is the same as the direction of propagation of the wave, which makes this wave not to be a transverse wave, but the longitudinal wave. So other properties on this wave are, if you see here the way this picture has been made, this part here, it means the particles or the wave is compressed. Then here it's not compressed. So these parts where the wave seems to be compressed, like a lot of particles are concentrated here as here. So this part, we call it first, this part which is not compressed is called rarefaction, and this other one which is compressed is called compression. So if you see the wave, there are parts where the wave seems to be concentrated, and the other parts where it's not that concentrated. So here where it is concentrated is called compression, and here where it's not concentrated is called rarefaction. So these are the two parts of a sound wave. So one truth about sound waves is they travel through matter. They propagate through a medium, and that medium should be matter. They are different from other types of waves, which we are going to discuss. For example, light waves. Light waves can propagate even when there is no matter. But for sound waves, they can only propagate when there is matter. If you go in the outer space where there is no solid, there's no liquid, there's no gas, when you speak, your voice won't go anywhere because there is no matter for that sound wave to propagate through. So this is the first fact about sound wave. So sound wave travels in matter, not in vacuum. Then, depending on the density of the matter or of the medium through which the sound wave is going to propagate, the speed also varies. The denser the medium, the faster the sound wave is going to propagate. So if you look at the three states of matter, solid, liquid, and gas, you should expect sound to travel faster in solids, then in liquids, then in gases. The simplest way or to remember or just to appreciate this is if I don't know if you have been in a situation where you had pressed your ear against the floor or against a metallic bar which is long. What you're going to see is if if it is on the floor, the footsteps of someone who is very far can be heard. Okay, but when your ear is not pressed against that floor, you won't be able to hear the footsteps. That shows that sound travels faster in solids because the floor and everything, the ground where the person who is far is stepping on is solid. So sound travels faster in solids, then in liquids, then in gases. So next we're going to study the speed of sound. So it has been measured that the sound travels at a speed of about 340 meters per second in air. Of course, under specific condition, for example, there is a pressure where this is true. At different atmospheric pressure, this is not true. But this is a standard number. So sound travels at a speed of about 340 meters per second in air. So how do we determine the speed of sound? There are two experiments that we can do. The first one is called the direct method. So we're going to start with the direct method. So in the direct method, we've got two people participating. One is we're going to call him observer A, and the other one we're going to call her observer B. So observer A has got a pistol here, and the distance between observer A and observer B must be measured, and it is we can call it as S. Remember, when we are studying equations of motion, we have a tendency of using S to represent the distance. So this should be an open field without anything here, because if there is anything here, it's going to affect the propagation of sound. Then second precaution, make sure that these two people are as far apart as possible, maybe 500 meters or 1 kilometer apart. Why? The reason is simple. What we're going to do is this gun is going to be fired. When it is fired, this person has to see that it has fired through the flash of the pistol. So when it is fired, there will be like a fire that has to be seen by this observer. Then the sound shouldn't be heard. That's why this should be as far apart as possible. So when this has been fired, it should take some seconds for the sound to reach this person. That's why they should be as far as possible. So what's going to happen is observer A is going to fire a pistol. Then observer B, upon seeing the flash from the pistol, she is going to start the stopwatch. When that happens, she'll be waiting for the sound of the pistol. When she hears the sound of the pistol, she's going to stop the stopwatch. The time taken between the firing or the point at which the flash was observed to the time the sound was heard is recorded as T. And the speed of sound can then be calculated using the formula V, which we are using as the speed of a wave, is equal to distance over time. So this is not a new formula. Remember this formula, speed equals distance over time. This is a general formula for speed, distance, and time. It's just that distance we're using S here and speed we're using V. So that's how we calculate the speed of sound. Then method 2 is called the echo method. So this is the setup for the echo method. So we are going to have observer A and observer B. So observer A is going to be clapping, then observer B is going to be recording time. Then in front of both of them, there should be a large and flat hole. So what's going to happen is when observer A claps, the sound is going to go. When it goes, it's going to hit into this hole and it's going to bounce back. And this observer is going to hear an echo. So we're going to calculate the time it takes for the sound to travel from here to here and back to the observer. Okay, so the distance between observer A and the hole should be measured and recorded as S. So how it's going to be done for accuracy, we're going to the observer A is going to clap about 50 times. So observer A is going to do the initial clap. When the sound goes, bounces back and reaches observer B's ears, then the observer B has to start the stopwatch. Then this one has to continue clapping for 50 times. Okay, it can be any number, 40 times, 30 times, but in this case, we're going to use 50 times. We just want to have a large sample, an average for those who understand statistics. Sometimes for you to have an idea of what's happening, you need to do a lot of measurements. So when you do, after the end of the 50th clap, then observer B is going to stop the stopwatch. The time is going to be recorded as T1. So once that time is recorded as T1, the time it took for a single clap to move from here where it is being generated to the hole and to come back is calculated as T, which is the time we're looking for a single clap, is equal to the total time for 50 claps divided by 50. Okay, so the total time we divide it by 50 so that we get the clap for a single one. So this time is the time for a single clap, like I said. Now to calculate the speed of sound, we're going to use this formula. So I want you to be, in short, it's going to be the same formula, but the distance is going to be twice the one we measured. Why so? Because when a clap has been generated here, the sound from it is going to go, covering the distance S, then it will go back, covering the distance 2S. So the total distance is 2S. One when going, the other one when coming back. Therefore, the formula is going to be V is equal to, another mistake I type in here is supposed to be 2S over T. The T is this one which you get from here. Then you are going to put it here. Then the distance should be 2S. 2S, that's the distance. So this is how the echo method is done. So finally, we're going to take a look at two properties of sound. The first one is called pitch. So the pitch of sound is defined as the highness or lowness of sound, and it depends on the frequency. So remember, frequency is just a property of a wave, which is the number of waves per second. So that's what pitch depends on. To understand this, you can say girls have a high pitch, boys have a low pitch, because the sound of girls has a higher frequency than the sound of boys. Okay? So that's what pitch is. When we talk about pitch, we talk about what differentiates the sound or the voice of boys and the voice of girls. So low pitch is low frequency and high pitch is high frequency. Then another truth about frequency is a man can listen sound waves with frequencies ranging from 20 Hz to 20 kilohertz or 20,000 Hz. So any frequency which is below 20 Hz or above 20,000 Hz is not audible. This range, 20 Hz to 20 kilohertz, is called the audible range, and any frequency below 20 and above 20,000 is called inaudible sound. There are some animals that use inaudible sound to navigate the world. I think a good example is a bat. Yeah, if I'm not mistaken, a good example is a bat. It uses inaudible sound. Then there were also some people who had created a whistle for calling dogs. It was a special type of whistle which would produce a sound which was not within the audible range. So if I've got a whistle, I could blow it. No one is going to hear anything other than my dog. Okay, so it was called a silent dog whistle. A silent dog whistle. So it was a whistle that only dogs could hear. interesting. Finally, we look at loudness of sound. So the loudness of sound wave depends on the amplitude of the wave. So if the sound wave has high amplitude, then that sound is going to be loud. Well, if the sound wave has a low amplitude, that sound is not going to be that loud. So this marks the end of this topic. It could have taken less time, but I wanted to be slow in explaining so that you get all the concepts. Hope you have liked it. Happy solving.